All right, let's make sure the audio's good. Beautiful. Let me pull up the little camera control. Mm. And oh, wrong one. It's a little better. Mm. All right. We're back for kind of the last section of this first week. So we looked at separable equations. We looked at linear first order equations. We looked at exact equations on that last lecture. So this last section, they call it substitutions. And so what I'm going to do with this last section, so in some sense, I kind of hate this last section because it does something that textbooks often do in mathematics, or at least once in a while, that I think is really frustrating. And that so what this section does essentially is it gives you two different types of differential equations that are ultra specific and also are kind of hard to tell. Like the type on them, it's kind of hard to tell what like the qualifications for this differential equation being this specific type are very precise. So they kind of give you these ultra specific equations that have a very ultra specific um, way to solve them that only works for that exact type of equation. So like I said, with the last lecture we did exact equations, so it gave you weird solutions, gave you implicit solutions, but at least it worked on a decently large set of differential equations, right? You just needed your coefficients in front of dx and dy. You needed the derivatives of those partial derivatives to match. You can construct a lot of differential equations that works with. And then going back to the section before that, um, the first order linear differential equations, you can construct quite a few equations. Yeah, and I say quite a few, I mean a lot. You just need a dy dx plus some, usually function of x times y equals something else. And you can use that beautiful, what do they call it, integrating factor that they developed, and go and solve it. So there's a lot of equations that works for. And the same is separable. There's a decent number of equations that are, algebraically they're separable and you need to use them. So to me, those three sections, the methods they teach you are crazy useful because they work on a lot of things, right? Um, then you get this section. So 2.5, you're going to get this section where you have two very ultra specific types of equations that don't pop up very often, or at least, I mean, one of them historically pops up, but there's just not a lot of equations like it. And they're going to show you for each of them a very ultra specific way to solve them involving substitutions, hence the name of the section. So anyway, so I hate sections like this because I don't think it profits you guys much. It just doesn't advance your math ability, your math technique, your critical thinking. It just doesn't do that. It's just sort of like recognize this ultra specific thing and remember this ultra specific thing. Anyways, so a valid question is, why am I even doing a lecture on this? So I'm doing a lecture on this for two reasons. One, you'll see with both these ultra specific type of equations that the substitution we're going to use then reduces those equations to two previous types of equations, differential equations that you've seen. So essentially it gives you practice with one of the methods that you guys saw in 2.3 through 2.5. So each type of equation will give you practice in one of those methods. So there's a cool conceptual connection to the previous stuff, and it gives you practice. And like I said, one of these types of equations is actually in the history of especially physics, both physics and chemistry. It's an important type of equation. Again, it doesn't actually come up a lot, but it's an important type of equation as far as the development of chemistry and physics. So so basically, especially because of that last reason, when you teach differential equations, you kind of have to teach these things because they're important historically. But like I said, these are not gonna hugely advance your technique or your knowledge of differential equations or anything like that. The best they're gonna do is give you a really cool callback to something you already saw in sections 2.3 and 2.4. So the way I'm gonna do this section then is you'll see on this homework, actually, this is a homework, there are 4 questions on the homework. 2 of the questions are of the first type of differential equation we're gonna talk about in this section. 2 of the equations are of the second type. For each type, so there's basically one general differential equation and there's one with initial solutions. So what I'm gonna do with this section is I'm not gonna try to talk about a bunch of concepts and get, you know, get you to connect on why the technique works for each of these types of differential equations. I am just simply gonna show you, hey, if you've got this type of differential equation, if it's doing this, if it looks like this is we're gonna do this technique. And if it looks like this, we're gonna do this technique. So much so that I literally am only gonna do 2 examples for this lecture, so it's gonna be a short lecture. I'm gonna do 1 example for the first type of equation. I will do 1 example for the second type of equation. You guys know how to deal with initial conditions now, so I'm not even gonna do a separate example with initial conditions. You guys can handle that. I am just gonna do the one and the other, and we're gonna call it good. So let's do that. So they call this section substitutions. And again, you'll see why, but spoiler alert, it's because these differential equations, basically what we're gonna do is, we're gonna, for each of them, there's a clever substitution you can put in. And once you put in the clever substitution, then the differential equation reduces to another type of differential equation that we've seen before and we know how to solve basically. Um, so kind of in some ways, at least strict, not concept wise, but strategically, kind of like we saw with the first order linear differential equations, where there was that integrating factor. That wasn't a substitution, but still it was a clever thing that we introduced to the equation. We multiplied both sides of the equation by that allowed us to simplify the equation we were looking at into another type that we could deal with much easier, or at least something we could deal with much easier algebraically, et cetera. So that's the same thing here. Each of these types of equations just has a very ultra specific clever substitution. And that substitution is going to make our equation at least eventually a lot easier to deal with. And like I said, spoiler alert, it'll make it like one of the previous types of differential equations that we've seen. So let's look at the first type. So type 1, not even, and so type 1, so if you see in the, if you look in this section, they call this first type homogeneous, it would be linear, or it would be homogeneous first order differential equations. I'm actually going to shy away from using that word. Let me tell you why. So the homogeneous they're talking about here, they're actually talking about the coefficients that you see in front of the dx and dy and that they are homogeneous. However, literally the next lecture we're going to talk about that we're going to have next week is about homogeneous linear differential equations, and the definition of homogeneous there is different. So the definition of homogeneous they use here is correct for functions, but not correct for differential equations. And so I actually want to shy away from using that word just because I don't want to confuse you guys. I'd rather the homogeneous that we're going to talk about next week. That's the thing I really want you to know for this class. That's the definition of homogeneous for this class. So I'm not going to use the word today. Just going to call it type 1. But let's look at an example of one of these equations. Dx is y minus 2x dy. And this is exercise 3, by the way, in the section. Y plus 2. All right, so this would be an example of this first type. So again, your first two problems, I think it's 4 and 14, for your homework, they are this type of problems. And I do want you to notice, so we want to compare and contrast. We're not going to compare this to previous problems we looked at. This looks a little bit like what we saw with exact equations, but if you took derivatives here, it wouldn't be an exact equation. So the thing is not that this does sort of look like an exact equation, and it could be, as long as our derivatives, our partial derivatives sort of match, but they're not going to match here. Part of the reason this looks like an exact equation is because in our exact equations, we often saw y's and x's mixed as part of our variables. And if you go back to what I talked about with linear first order differential equations, that was one of the things I kind of remarked, that to be a linear first order differential equation, you need your coefficient to only involve x and also involve y, right? And your y definitely can't be squared or anything like that. That's not linear, quite literally. So what you're seeing here, and actually technically what we saw in the last section, which I think I just didn't occur to me to mention. But what you're seeing here especially is that my coefficients now are functions of both y and x, or they include y, function y. Again, so this is going to be your tripwire to say this is definitely not a first order linear differential equation, because because you have a mix of x and y here. Also, honestly, because of this subtraction. So just to, so you kind of see, again, you're going to be doing this homework and you'll just know what type it is, but that's a little bit of the difference here. There was, so you've got a mix of y and x's here. So basically, for this section, when you see that, actually, let me see if is that consistent with the other type of equation. Yeah, it's kind of. Yeah, I think that's actually roughly this section. So don't quote me on that, because I could theoretically be wrong. There could be some equations that fit these styles that don't. Anyways, but that's pretty consistent on this section actually. So you're seeing functions of both y and x as part of your coefficients, and there's no way. Again, going back to the beginning of this chapter, there's no way you can also separate out things. So you can't separate these out into x's and dx's on one side and y's and dy's on the other side. Anyways, so this first equation, kind of get to this, you get this, and I can't separate the thing, and it's not an exact equation. It's definitely not first order linear differential because of the y's and x's. So what do I do with this? So like I said, there's a very ultra specific substitution. There's actually two ways we can do this, but the substitution they're going to use here, substitution we're going to use here is, so basically what we're going to do, and again, this is where, because these are so ultra specific, I don't want to get into theoretical and the conceptual, like why would you make this substitution? Why would you do this thing? How does it work? Why does it connect? It's just not good. You likely wouldn't get it, and it would take a ton of time to not get it. And all for one or two specific pattern problems that you're rarely ever going to see. So but the idea is, so like I said, one of the main issues that's happening here is that these functions are of y and x. And so what we're going to do is we're going to make a substitution where we declare y to be some function of x using now a new variable. So so in some sense we're saying y is dependent on x, but it's not a coefficient times x, it's a new variable times x. And you also, let me make sure I get this right in the book, there's two different substitutions that you can use here. Let me make sure I write these down correct. Or x equals, yeah, okay. So basically, the substitutions that you can use here, you can either make y dependent on x, or you can make x dependent on y. And the letters of these other variables don't matter, but just know that you're making it dependent on x, but not a coefficient times x. You're making it actually a whole other variable times x. So y, we're either going to declare y as u times x, variable times x, or x as a variable times y. Now, one of the things that I'll mention that they also mentioned in the book is you don't know up front which of these substitutions is going to be sort of the better play. So basically, sometimes what happens is you'll use one of these substitutions and you end up, in the work that we're going to do, you end up in a place where you kind of can't do the integrals from there, basically. If you can't do the integrals, that's actually your sign that tells you to go back and use the other substitution. And unfortunately, there's just not a good way to know. There's not a good tell, basically, to begin with, on which substitution is going to be your better play. So you've got to be okay with picking a substitution, going with it. And if you get to a place where the integrals don't work, go back and choose the other substitution, and that should be easier, and you'll get integrals that work. So you're going to be okay with a little bit of trial and error. So I always tell students in all my math classes, that's maybe we would like it that all mathematics has no trial and error, right? That we found a method, a solution, a logic for every single situation. And that, in some ways, that's the goal of mathematics. That hasn't happened. It doesn't mean it won't happen. It also doesn't mean it will. Maybe trial and error is a natural part of logic and life. Maybe. So just know that especially at this level of mathematics, you would expect everything to be theory and have a nice procedure and a pattern. And not always. Sometimes you still got to do trial and error. All right. Anyways, so I'm going to choose this substitution to begin with, but just know that it's one of these two that you use, but you got to pick one. Once you've picked one, what you want to do is you want to take the derivative of both sides of your substitution, and we're going to mark it using dy's and dx's. So we want to do the derivative of y. And if you notice now, the way I'm reading, with this substitution, the way I'm reading y is two variables, but that means they're also functions, two functions multiplied. So if y is two functions multiplied and I'm taking the derivative of it, what's my pattern? How do I take the derivative of two functions multiplied? Good. That's the product rule or product pattern for derivatives. So that's the pattern where, again, if I have two functions multiplied, I'm taking the derivative. What I do is I do the first function times the derivative of the second plus second times the derivative of the first. So the derivative of this would be u dx plus x du. And then the clever thing that I'm going to do here, so the reason I call this substitution, so now that I have sort of this info, I'm gonna go back into this equation and everywhere I see a y or a dy, I'm gonna make these substitutions. And it may seem like, again, it may seem like you're just swapping one variable for another. And so one, I will say logically, in truth, yes, that's what's happening. Our hope is that by swapping one variable for another, we actually end up with a different form, or we basically end up with an equation that we can that we can take that we can solve, basically. Because again, the motivation for this section is you look at this, it doesn't fit any of those first three patterns that we saw. It's not separable. It's not first order linear, and it's not exact. So we're using this substitution to basically another tool. And see if we can get it. See algebraically if we can get it to a form where it does work. So let's go ahead and do that. I'm going to replace my y's with ux. I'm going to replace my dy with this. So we end up with x dx plus ux minus 2x parentheses. Then my dy is u dx plus x du. All this equals 0. Now I'll give you kind of the end from the beginning. I'll give you the spoiler on this type of equation. So this first type of equation, again, the first two problems that you guys have seen in this homework. The point of this is that your substitution should actually make this. So this looks horrible, and we got to do a bunch of algebra. But the point is, algebraically, you actually should be able to make this into a separable equation. So again, that first type of equation that we learned, differential equations, that, like I said, has pretty broadly applicable. The point of this substitution is you're taking something that is not separable, or first order linear, or exact. But by doing this substitution, I'll say magically, seriously, it actually turns it into a separable equation. And then we can go ahead and solve it. So that's your goal. Again, on these the first two questions on your homework, these very ultra-specific type of differential equations with this ultra-specific substitution, but they've just figured out that in these few cases with this substitution, it turns it into a separable equation, and we can solve it. So let's see if we can get there. So that's my thought, is that by doing the substitution, this should be separate. Which means now what I have is x's and dx's and u's and du's, and I need to get the u's and du's on one side and the x's and dx's on the other. So first of all, we got a good bit of we got a good bit of distribution to do here. I'll see algebraically if there's a way out of this without doing all the distribution. Probably not, but that's all x's. Well, no, there's a probably not. So let's go ahead and do the distribution. So we have x dx, we got ux times u dx, so u squared x dx. We've got ux times x du. So u x squared du. And then minus 2x times each of those, so minus 2ux dx minus 2x squared du. All this equals 0. So I think, going back to how we dealt with separable equations, we were trying to get, again, all of our, in this case, x's and dx's on one side, u's and du's on the other side, which means initially, I need all my dx's on one side and all my du's on the other side. So let's kind of do that. I'm going to keep everything that has a dx on the left, everything that has a du, I'm going to move that to the right. So that what I'll end up with is x dx, let's see, where's the next one, plus u squared x dx minus 2u x dx. Well, that's nice. They all shared x dx in common, so that's actually very promising. And on the other side, we're going to get 2x squared du. Sure I got that multiplication right. Yeah. I'm missing something. So 2x squared du minus ux squared du. And then we can start doing some factoring here. So let's see, on this side, like I said, I just noticed that there's an x dx in common for everything, so let me go ahead and factor that out. So we have x dx. Doesn't matter which way you write this, but let me do, this would be u squared minus 2u plus 1 x dx. And on this side, it looks like they have an x squared and a du in common. So this is going to be x squared 2 minus u du. Notice I'm actually pretty darn close to having all my x's and dx's on one side and vice versa, the u's and du's on the other side. Facts. So then what I can do is I can divide this off, bring it down on this side, and I can divide the x squared off of this side. So I'll just have that. Dividing these. And I'm just doing the same thing on both sides. So what I end up with is 1 over x dx on this side. I end up with 2 minus u I'm just thinking for I'm actually going to turn this into u minus 1 squared du. So now we do have x's and dx's on one side, u's and du's on the other. Again, notice the craziness of this. So like I said, at the beginning, we didn't try to do it, but I'm sure you guys can go back and look at it, see that you're not going to be able to get the x's and dx's on one side and y's and dy's on one side. So it was not a separable equation. But somehow making this substitution makes it a separable equation. And that should blow your mind for a second. And let it blow your mind. It is really weird that that works out. Again, there's some deeper mathematical reasons for it, but I won't promise you, but I'd be willing to bet the person who first discovered this honestly was just trial and error. They were just playing around with things. And they happened to see that this worked. And they happened to see that it worked every time on a certain, type of equations. And then they probably went prove theoretically that it should actually work every single time. But I promise you this likely was just somebody playing around algebraically, just trying to make something work, figure out something that does work. So, all right. So then what we have to do is take the integral of both sides. This is where, give me a second. I think this is where we've got to. Yeah, I don't. I'm trying to think of this, the method for integrating here. I want it to be something simple. It's probably partial fraction decomposition. Just pretty horrible. I mean, not horrible. They put this in the book. You need to do everything you kind of calculus, but that takes a second. All right. So we're probably gonna have to do partial fraction decomposition for this. So the left side is easy to integrate. So what I'm gonna do is let me do some work over here just for this specific part. We'll kind of add that answer in. So for this part, what I'm thinking is this partial fraction decomposition. By the way, I'm thinking that because what I tried to do initially in my head was break this into two fractions, so it'd be 2 over u minus 1 squared, and that part you can't take the integral of. But the u over u minus 1 squared, that's the problem. That part you can't take the integral of. You can't use substitution method on that. And I don't think you can use the integration by parts on it either. So that kind of leaves partial fraction decomposition, especially when you see a fraction like this and nothing else is working, that kind of narrows it down to partial fraction decomposition. The partial fraction decomposition says that I'm basically this part, I'm gonna do a little system of equations to try to figure out what do you call it? What two fractions added together give me this. This fraction has u minus 1 squared as a what do you call it? As a denominator. So what I'm going to have to do is this, saying that has to equal a over u minus 1. Plus b over u minus 1 squared. Yeah, I'm sorry. So to make this a common denominator, then we're saying that this has to be multiplied by u minus 1. So a times u minus 1 plus b has to equal 2 minus. So the two possible fractions I can have that sort of add together and still give me this common denominator. One of my possible denominators is u minus 1. But when I try to add these fractions together, I would have to multiply the top and the bottom by u minus 1. So what this tells me is au minus a plus b, that has to equal 2 minus u. And then we can sort of start to make things equivalent here. That means a has to be -1, has to match that coefficient. So a is -1. And if I know a is -1, what also has to be true is -a plus b has to equal 2. So I will plug in -1 for A, which gives me a 1. So 1 plus something has to equal 2. So that means B equals 1. So A equals -1, B equals 1. So what this allows me to do then is I can literally rewrite what I see here with this, which is -1 plugged in for A and 1 plugged in for B. So I'm really doing the integral of -1 over u minus 1 plus 1 over u minus 1 squared du. And notice that now each of these I can take the integral of. Just a very, I would not even a review of partial free fraction decomposition. I literally would not have the time, unfortunately, especially in 5-week course, to kind of sort of re-up you guys on it. So hopefully that this makes sense and that is enough to jog your memory on partial fraction decomposition, but that is the thing you're gonna have to do. So what I have now is I'm gonna sort of bring all this up here. And I know this is a mess, and I'm sorry, this is just sort of how this works. But now what I have is the integral of 1 over x dx equals that. But now I have things on the left and the right that I can actually do the integral of. So what I'd like you guys to do is go ahead and pause on your side and go ahead and do these integrals. If you feel like you have an idea algebraically how to work it forward from there, that's fine. But you don't even have to do that right now. We'll do that in the next step. Right now, I just want you to take the integral of both these sides. So go ahead and pause on your side. I'll pause on my side. Let's see what we get. Typically on the left side, it's very obviously natural log or absolute value of x. And then on the right side, we actually have similar, at least the first part is a similar result, right? So 1 over u minus 1. So that's going to be negative natural log of u minus 1. And this next part, this is u minus 1 to the -2 power. So it's actually, so we're going to end up with u minus 1 to the -1 divided by -1. So this is going to be minus u minus 1, well, 1 over u minus 1. Write it that way. All plus c. So you've taken the integral. So again, the successful thing about this is now the left side, we could separate the left and the right side. And so we could take the integral of the left and the right side. So now we're there, but not there, we're almost there, because we still got to go back to this equation started with x's and y's. And again, really the goal of my differential equation then was to solve for y, right? So have some sort of, or at least an explicit solution would be nice, but maybe even like the last section with exact equations, at least an implicit solution. Some mix of x's and y's on left and right side of the equation. And I don't have that right now, I have these u's. So then our next job is we got to go back and replace u. So again, using our substitution, we got to replace u. So you can see, hopefully you can see pretty easily from this that u would equal y over x. So everywhere I see a u now, I'm going to replace it with y over x. Y over x minus 1 minus 1 over y over x minus 1. And then pretty much from here, you're going to try to, you want to see if you can solve this, make this explicit, get the natural log by itself. Or sorry, not natural log, the y by itself. But if you can't, you at least want to algebraically simplify this as much as possible. So So something you might be thinking as I'm going through this is, holy, like this is a lot of algebra. Just a lot of the integral part of it. Actually, the actual calculus that we're doing is a very small part of this. The rest of this is just a crazy load of algebra. So we did a little derivative here, we did a little integral here. The rest of this is algebraic manipulation. And unfortunately, that is the nature of this problem. So again, another reason that I actually didn't want to focus on this section. That is the nature of these problems, and just kind of is what it is. So, I think a couple things that happen here, a couple things we likely do. Actually curious too. So I have a solution in the book that I think is equivalent to what we're going to get. Not just think, I mean, it is going to be equivalent to what we get. But I wonder if they are, what are they doing here? Yeah. So one thing I'm going to do kind of algebraically to start simplifying things is we have this y over x minus 1, and I basically want to make that a much, not only more readable form, but maybe better form to deal with algebraically. So what I'm going to do is, 1 I can rewrite as x over x, and then I can combine this into one fraction. So I'm going to rewrite, so natural log of x, negative natural log, absolute value of y minus x over x. So that's basically, that's going to become y minus x over x. And the same over here. This is going to be 1 over y minus x over x. And so to save us a line, I want you to see that, which means I can 1 over just means I flip it over. So this is really going to become x over y minus x. I think what I also want to do is I want to move this negative up as a power here. And if I move it up as a power, that's a -1 power, which is 1 over, which means that also flips over. So essentially, we can transform this into, again, without getting into details about absolute value functions, we'll just say we can do that. And then, like we've seen with a couple of our problems in the last several sections, so then what I'm doing here, well, give me a second, hold on. There might be a better way to do this. Oh, there is a better way to do this. Thank you. So then what I'm going to do is I'm going to subtract. So I didn't even have to do that. Look, give me a second to see if it was better to leave it previous way. I mean, it's the same thing either way. Yeah, actually. So this is fine, this would work, but let me actually save us a line of work there that I already wrote. But what I'm going to do is I'm going to move the natural log to this side, so then I can use the properties of natural logarithms of logarithms to combine those. So we're going to get natural log of absolute value of x plus the natural log of the absolute value of y minus x over x. All this that equals negative x over y minus x. And when 2 logs are being multiplied, then I can multiply the pieces, I can turn it into one logarithm where I multiply the pieces inside. Notice that I'm going to have x times y over x, y minus x over x, the x's cancel. So I'm just going to end up with natural log of y minus x. And I'm sorry, there was a c here. Let's see, have we done anything? No, we've just done, yeah. So that is still there. Plus c, so negative x over y minus x. plus C. Or C minus that. And then to get the form that you guys will see in the book, but basically the last algebraic manipulation that they would do to kind of make this look nicer. Again, this, like I was talking about in the last lecture, I think it was y'all's class that this is more aesthetics than anything else. Is maybe you want to multiply by y minus x just to get rid of this denominator, and because you'll just end up with a y minus x on the main line here. If I do that though, if I multiply by y minus x, I have to multiply both pieces on the right here, including the c. So multiplying by y minus x, what you end up with is, so you end up with y minus x natural log y minus x equals, I guess it'll be c. So I'm going to rearrange it just so the negative's not out front, but c times y minus x, and maybe you can move the x to the other side, but either way, that's your answer. And yes, that is a lot of algebra to kind of get to the point, and that is sort of the nature of these problems, like I was saying. But that is this one type of ultra-specific problem in this section. And again, the hopefully Oprah moment for you in this is that this substitution somehow turns this into a separable equation, which is kind of nice. So it's pretty amazing that substitution. It's a relatively simple substitution too. So it's pretty amazing that substitution turns something you couldn't work with to a separable equation, which usually is really easy once we had a crap load of algebra to do, but nonetheless, it's usually pretty easy to work. All right, so that's one type of equation you're going to see here. So like I said, 4 and 14 are just these types of equations. You just gotta play them through. All right, then the other two problems that I gave you for this homework, 16 and 22, they are of another type of equation. And so we're gonna do, give me a second, which one do I want to do here? I think I actually want to do, well, the thing is, this doesn't actually need, wait a second, this doesn't actually need this particular method. Oh, yeah, so we're gonna look at problem 15 for this other type of equation. So this other type of equation, by the way, so they call this, make sure I spell this right, a Bernoulli equation after a scientist named Bernoulli, physicist, I believe. These are Bernoulli equations. Let me show you what kind of distinguishes these equations from other ones you've seen. X divided x plus y versus this Mars. Yeah, sorry, I'm sorry, guys. So 15. Yeah. Okay. All right. So again, so that last type of equation, or the first type in the section, again, they tell you in the exercise which type it is, but the first type, what do you call it? It wasn't separable, it wasn't linear first order or exact, but we found we had a specific substitution that we could use that actually turned it into a separable equation. So it kind of like took you back to section 2.2, right? This equation. So taking a look at this, what type of equation that we've seen so far in this chapter does this look like, kind of off the cuff? Good. So hopefully you see this actually looks kind of like a linear first order equation. In fact, if you divide by x, like this left side is going to look exactly like what you would normally see for a linear first order equation. So there's sort of some instinct that we should be able to solve this like a linear first order equation using, your integrating factor. However, what is different about this compared to a linear first order equation? And hopefully you're seeing that the right is hella different. So in a linear first order equation, your right was always a function of x. Here we have y on right, a function y. And specifically, specifically a Bernoulli equation. So the thing is, to be a Bernoulli equation, you can't have any type of y thing happening on the right. So to be a Bernoulli equation, it has to be very specifically, you could have some x's on the right, that's fine, but your y that shows up on the right has to be a power function. It has to be y to a power. And that's, actually, let me see. Let me look at the definition. Maybe we can have decimals, but I don't think so. Look at the definition again, though. Yeah, no, they have to be integers. It has to be a power function. So that is the very specific catch here. So like I said, that's why this is incredibly specific type of differential equation. This on the right, you can have x's, you can have a function of x, whatever you want, but this specifically has to be y to a power, which in this case is y to the -2 power. It has to be to an integer power. They make a note in the book if this power is 0, so if this is y to the 0, which is 1, or even y to the 1, this actually reduces to first order, like it's already a first order linear differential equation. But otherwise, it isn't. So that's the big difference is, again, with first order linear differential equations, we didn't have a function, we didn't have y on the right side, we didn't have a function of y on the right side. But here we do. But as long as y is specifically y raised to a power, then it's what's called a Bernoulli equation. This is a differential equation that Bernoulli figured out worked for a lot of, pretty sure this is fluid flow. Pretty sure this is fluid flow. But anyways, so he kind of solved this equation coming up a lot in this very specific case, and he devised a way to solve it. Now, the way to solve this. So again, like I said, this section is about very specific equations with very specific substitutions. The thing is, again, this is not a linear first order equation because we have function of y on the right. However, it's pretty close, right? So the interesting thing about this substitution that we're about to do, this very specific substitution that Bernoulli figured out worked, it reduces this to a linear first order equation. So it's going to reduce this to kind of what we think it is or what we want it to be, right? And then if you think back again to section 2.3, then we can do, or I guess that was 2.4. We can do, no, 2.3. So once we put the substitution in and it's become a linear first order differential equation, then we can do the integrating factor on both sides and do all that. So that's when you see these equations, that's your goal in your head. You already have this kind of laid out in mind that you make the substitution, do the work, and then but what you're looking for is that once you've done the work, it should be a linear first order equation. And you can do the integrating factor. So again, just like on the last type of equation, you did the substitution, and what you were looking for was a separable equation. You were figuring that you should be able to separate it. So these are going to become linear first order differential equations. Now the substitution. So the substitution we're going to use. Substitution is very specifically y u equals no, what was it? Y or u? That should be, yeah. Yeah. Yes, u equals 1 y to the 1 minus n power. And n being whatever power you have for y here. So in this case, for instance, 1 over y squared, it means this is y to the -2 power. So I'm going to plug in -2 for n. And that gives me, in this case, u equals y to the 3rd power. And what am I doing this? I guess we can do this either way. So that's our substitution. Like the last problem, so once, and not just the last problem, anytime in mathematics that we're using substitutions. So once I have this, I need to look at you basically got to look at the pieces here that you're gonna have to replace, right? So I'm gonna have to replace a y here, a y here, a dy here. I need to know what y and dy are out of this. So the first thing I'm gonna do is rewrite this as cube root of u equals y. So that tells me y equals cube root of u. What this also allows me to do is now I can take the derivative of both sides. And so dy is going to be out of derivative of y. The question is, what is my derivative of the cube root of u? Which again, we're treating u actually more like a function. So realize that u is inside a cube root, right? So you're going to use a little bit of chain rule there. So I'll actually give you guys a second. I'm not going to pause, but just take a second and work out this derivative here. All right, so should get from u to the 1/3 power. So this is going to be 1/3 u to the -2/3 du. And what we'll see as we go through the problem, I will honestly probably leave it like that instead of trying to do a fraction, because it'll likely make some of the algebra easier. That was the initial part here. So y equals this, dy equals this, and let's go ahead and plug that in and start having fun with algebra. We're going to end up with x. Well, yeah, so let's write this way, x dx, and then it's going to be times 1/3 u to the -2/3. Maybe we do want this as a fraction. Then I'm going to add y, which is the cube root of u. So maybe make that u as 1/3. This all equals 1 over a y squared. So that's going to be basically u to the 1/3 squared. And notice that that's going to be u to the negative 2/3. So again, what I'm going to do here, I want you to see this. But again, we've done enough algebra and calculus. You guys should be able to play that out kind of in your head or really quick on your paper. So that's u to the negative 2/3. So then what we're going to need to do, so now what we have is, now we have a differential equation in terms of u and dx. And we, again, the instinct here is this actually should reduce down to a first order linear differential equation. Which means what I want to see is a couple things happen, but I'm going to need to see, I guess, either du dx or dx du. On one piece here, I'm going to need, I guess it's whatever variables on top needs to be over here with the other variable in front of it, and then the other variable has to be over here. So I mean, I'm sort of saying that hopefully maybe visually that makes sense to you, but that's what I'm going for. Is I see a picture in my head of what a first order linear differential equation in general looks like, and I'm going to try to use algebra to make that match. Let's see. How am I going to do this? Actually, this dx on the bottom is kind of an issue. I think what I'll do actually, since this dx is on the bottom, I'm going to go ahead and multiply through by dx. Is that going to help me or not? At least we can subtract the 1/3. What did I do wrong? -2. That's fine. Oh, the PU is already part of that. Oh, right. I saw that as separate. Okay. Let me do a little rewriting. Maybe it will be helpful to see this bottom of the fraction. Let's just multiply it all together. So I'm going to end up with du dx times basically over 3 u to the 2/3. Let's at least write it that way. With an x, sorry, x over that. What I will also do in this move is I'll go ahead and subtract the u to the 1/3 from both sides. So that's going to be u to the negative 3/3 or u to the negative 1 over u. It's actually kind of what we need, right? So let me rewrite this part. Let me go back to the negative 2/3. I think that actually works. Doing something wrong here. What am I missing? Oh, I needed the u to the 1. x over 3. I have to use the negative 2/3 plus u to the 1/3 equals u to the negative 2/3. Then I think what I'll do is I'll multiply by u to the 2/3. Essentially, just maybe so you guys you can probably see it either way, but so I'll put u to the 2/3 on the bottom. So that was a good way. Then I'm going to multiply everything by u to the 2/3. Yes, to get rid of this. Because for first order linear differential equation, we're used to seeing, so in front of our derivative, if there's anything in front of our derivative, initially it's usually a function of x, so that we can kind of divide that off. So let me take this in steps, but I'm going to multiply everything by u to the 2/3. Oh, this is the magic. Magic of this is then these essentially cancel each other and you just get a 1 out of that. You get u to the 0 power, which is 1. U to the 2/3 also multiplies through here. So it's multiplying by u to the 2/3 there as well. So we end up with du dx times x over 3 plus 2/3 plus 1/3 is 1, so plus u equals 1. Good. And notice that, so the first thing to notice that now this is a first order linear differential equation. You have derivative, you have your u that we're now solving for, and you have not a function of u on the right side, right? We do have a coefficient from du dx, so with first order linear differential equations, when we did that section, section 2.3, you saw that you basically just divide by this, so you can get the du dx cleanly by itself. It's just a 1 in front. So we're going to divide by x over 3 everywhere. And what that does is it reduces this to du dx plus 3 over xu equals 3 over x. And once you have the du dx with cleanly a 1 in front of it, this is the standard form. And when we have it in standard form, what can we identify from there? What can we do from there? So good, kind of, again, jogging your memory to a couple lectures ago. This 3 over x then in front of u, that's your p of x, and we can make the integrating factor. So let me rewrite this up here, do the work from there. So du dx plus 3 over x u equals 3 over x. And this is my p of x. So I then can calculate my integrating factor. My integrating factor is e to the integral of that, 3 over x dx. And so now we have to figure out this integral and that integrating factor. And remember, once we have that integrating factor, we're going to multiply everything through by the integrating factor. And then essentially integrate from there. So let me have you guys practice that. So again, you've seen this, you've done this before. Maybe, hopefully, honestly, you've done this homework before you got to this lecture. I would actually suggest that as you go through this class, I know some of you probably like try to watch all the lectures and then do all the homework. The way this stuff builds on each other, it's honestly better that you watch a lecture, do a homework, watch a lecture, do a homework, watch a lecture, do a homework. So hopefully you've already done this homework for 2.3 before you're watching this lecture. But if not, just in the future, honestly, that's just probably going to be a better play for you. But go ahead and work this integral. This is my integrating factor. And then see if you can work out the rest of the problem. Multiply it through, do your integrating, all that kind of stuff. All right, let's see what he does. So First of all, the integral of 3 over x dx, what does that give you? So that'll be e to the natural log, actually 3 times the natural log. Oh, yeah. 3 times the natural log of x. Now, remember properties of logarithms, so 3 can go up as a power. So then this is going to be able to reduce. The e and the natural log are going to cancel, and you're going to get x cubed. We're just going to get a clean x cubed out of this. Lost around it, but good. So that's what I'm going to do then, is I'm going to multiply everything through by x cubed. Yeah, and I was just kind of playing it out in my head. This is pretty awesome how this works. Again, this little integrating factor for linear first order differential equations is just hilarious because of how perfectly it works. And again, there's some math behind that, but we just don't have the time in a class like this. But I'm going to multiply everything through by x cubed now. So now I'm going to have x cubed du dx plus, and x cubed is multiplied, when x cubed when you multiply by 3 over x, one of your x's canceled, so you're going to get 3x squared u. And then the same thing on the right side, we're going to get 3x squared. And then notice that, so again, if you forgot the whole play, the reason we find this integrating factor and we multiply it through, the whole reason we do that is what you're going to see here, what you're trying to see here, what you're going to see here is that this is actually the product rule. This is the product rule pattern for taking the derivative of 2 different functions. So the functions are x cubed and u. So here we have x cubed times the derivative of u. Here we have u, and if you think about it, 3x squared is the derivative of x cubed. So this is exactly the derivative of just x cubed times u. It's the same thing. And if it's the derivative of x cubed plus u, then I can take the integral, and it just gets me back to that. And whatever I do to one side of the equation, I'll do to the other. So we end up with x cubed u equals, and the integral of this is x cubed, actually just x cubed plus c. And then I'm gonna divide by x cubed. So what I end up with is u equals 1 plus c times x to the negative 3. And now, so it's great, you've solved it, right? But we've solved it for u, now we just gotta go back and replace it, or resubstitute things so I can get my y. We said that u equals y cubed, so I'm now gonna go back and replace this with y cubed. And voila, I have a nice, it's an implicit solution, but nonetheless, no, it's not an implicit solution. It could take, actually, I'm curious mathematically why the book didn't take it farther and take cube root to both sides, but let's see if I can figure out why. I guess that's probably just the way they prefer to write it. So this is correct. And also just go back and take a cube root of everything. So you end up with 1 plus c. I'll even write this. Let's be fancy about it. Let's write it as c over x cubed. Good. And that also says the same thing. Good. But that would be our solution to the differential equation. And again, so your other two problems, I think it's 14 and 22, are exactly like this. One just has some initial conditions for you to plug in once you get to this point and figure out C. So overall, again, this section is just about two very specific types of differential equations with very specific substitutions. So you're either going to get the first type that we did, where x's and y's are mixed, and again, they're going to tell you the type that it is this homework. They're honest to be not just nice, but they're basically not being sadistic. But this first type where you have a mix of x's and y's and it doesn't fit any of the other types that we've seen. But the point of that type is if you make that very specific substitution, basically y equals ux, then it becomes a separable equation, and you can solve it like you would solve a separable equation. And the other type is a Bernoulli equation. So again, the big difference here between this and a first order linear differential equation is that the right side has y, it's some power. And if you have that, this very specific substitution will reduce this to a first order linear differential equation, which you then can use that method to solve. And that's it. That's this section. Right, so good stuff. So that'll finish you guys off for the week. 2.2 through 2.5. Make sure you're hearing those homeworks by Monday nights. And I will have videos I'll keep putting up videos for you for next week. Just the small notes for this semester in particular. I kind of got my schedule changed pretty last minute. I'm making these videos kind of as we go, right? So just know that I may not have all the videos for week 2 up by the beginning of week 2, but I will have all of them up at least by Thursday for you guys. I should have the first video by like when Monday flips around, you guys should be able to work through the first video. So also for that reason, kind of take the or what do you call it, each week in this class, kind of take that approach where watch a lecture, do a homework, watch a lecture, do one. I know not everybody's schedule makes that possible, but if you can, kind of try to run it that way. All right, I'll see you guys for the next set of lectures for week 2.